Hey guys, so let's try and finish off chapter 9 and look at buffers to bring a talks to a conclusion for the chapter. Excuse me, just getting tangled in wires here. So we take a buffer, we've got a solution which resists a change in pH. So you add an acid, it stops the pH getting too low. You add a base, it stops the pH from getting too high. We're resisting changes in pH. And we see lots of fluids in the body which have a role like this. Your blood plasma needs to be maintained at a pH of about 7.4, neutralizing acid byproducts from your metabolism. Cell fluids have to be maintained at pH 7 neutrality. Saliva tends to be slightly acidic to help break down food in the mouth. Gastric juices are really acidic to help kill off bacteria and break down proteins in the body. Pancreatic juices often have to neutralize stomach acid, so they are basic in nature. Your urine can be a little bit acidic or basic. It's probably most of the time slightly basic, to be honest. So if you have to resist pH dropping by the addition of an acid and resist pH rising from the addition of a base, the best way to prevent or resist pH changing is to have access to both an acid and a base, And the best remedy for an acid-base solution is to have a conjugate pair. As we talked about in the chapter, a conjugate pair is made up of an acid and a base. It's exchange protons with other chemicals in the solution. So if we look at an example buffer, something like the ammonium buffer, which is in the kidneys, trying to maintain the pH of your urine. You've got a conjugate pair, which is mixed into water. So it's a non-water conjugate pair. Let me change pen color here. Let's do black. So we've got the NH4 and the NH3 making up that conjugate pair. So we know that the NH4 is an acid because to turn into its conjugate partner, it's about to lose a proton in this proton transfer for the forward reaction. Meanwhile, its conjugate partner, the NH3, we know it's a base because it's about to pick up a proton in the back reaction. And that's always what we see in these reversible acid-base reactions. Proton transfer in one direction, and then that proton transferred back in the opposing reaction. So the NH4 becoming NH3, this is our acid, and this is our base. Because we can write the equilibrium expression for the reaction, or the acid ionization constant, as it's known. It's always tricky with this pen, trying to use it, because there's an annoying button which is right in the middle of the pen, which I keep pressing. Acid ionization constant, products divided by reactants. Because of the aqueous conditions, we don't include water. We said that back in chapter 6. So there's an expression. And if we need, we can make hydronium ions a subject, because if we know what's happening to the hydronium ions, we can work out what's happening to pH, because pH is the negative log of hydronium ions. So the NH4 goes up as it moves across the equals, the NH3 goes down. So if we move over the page, let's take a look at a couple of examples of what can happen. Actually, Let me try and get the original buffer on the page at the same time. So I'm going to delete that briefly and make this a new page header. Then bring the stuff back. There we go. Just makes it a little bit easier if we keep everything on the same page so we can see. Again, there's a buffer we were talking about, the ammonium buffer, with a conjugate pair of NH4 and NH3. So if we add an acid to the system, as in nitric acid, now this buffer will bide its time in protecting the solution, exchanging protons with water. But if a strong acid is brought into the system, then we get an acid-base reaction. That external acid will react with the base, because the base of the buffer is that conjugate base NH3. So we see a proton transfer, as we would normally, from the acid to the base. So that proton transfer causes the NH3, just as it does here when it accepts a proton from hydronium ions which are present. It doesn't matter who is accepting a proton from. When the ammonia NH3 accepts a proton, it turns into its conjugate partner, the NH4, which is the conjugate acid of the buffer. So we use up a little bit of the NH3, produce more of the NH4. So producing more of the conjugate acid will mean that pH does still drop, but we've neutralized that strong acid that was added by using the conjugate base. So the solution resists that change in pH. It can't completely stop it, because as a consequence, we produce some of the buffer's own acid. Alternatively, if we add in a base like lithium hydroxide, we know it's a base because it contains hydroxide ions. A base will always react with an acid. Now the acid of the buffer normally, as it's passing the time, gives protons to water, but when a base is added, it will instead give protons to the lithium hydroxide. So that hydroxide ion picks up the hydrogen ion to form water, the lithium drops off, and it goes to NH4, giving away the proton, turns into the NH3. Doesn't matter who the acid is giving a proton to, whether it's water in the original system or a base which has been added to the system. It still gives away the proton and turns into its conjugate partner, NH3. Because that NH3, of course, is a base. And so although we neutralize the base that's been added, we still produce a little bit of the buffer's own base. So the pH will still be seen to rise. And that's it. That's how a buffer works. If you add an acid, it's the base of the buffer that comes to the rescue to neutralize that solution. If you add a base, it's the acid of the buffer that comes to the rescue to neutralize that base. Let's look at a couple more examples. Excuse me. Again, I'll rearrange my notes a little bit to get this at the top of a page, so we can keep the original buffer expression in. Okay. Let's use red this time. So again, you look at the buffer, and the first thing you should ask yourself is, what is the non-water conjugate pair in the system? Because that's the buffer of the system, H2PO4 and HPO4, dihydrogen phosphate and hydrogen phosphate. Now for the H2PO4 to turn into its conjugate, it's got to give away a proton, to water, it's acting as an acid. It's the acid of the buffer. And the HPO4 turning into its conjugate in the reverse reaction, it's got to pick up a proton from the hydronium ions. So it's definitely the base of the buffer pair. So if we add in potassium hydroxide, because potassium hydroxide is a base, it contains hydroxide ions. That base would therefore react with an acid. And of course, the acid which is going to save the day is the acid of the buffer. That's the H2PO4 dihydrogen phosphate. And so we see an acid-base reaction. That potassium hydroxide neutralized by the acid of the buffer, H2PO4. There's a proton transfer from the acid to the base. So the acid turns into its conjugate, just like it does when it gives a proton away to water, turns into hydrogen phosphate. The hydroxide picks up the hydrogen ion to form water. And we get that leftover bit of the potassium ion. And that's it. An acid-base proton transfer, just as we said in the Bronsted-Lowry theory. Still using the same buffer, let's look at another one. Let me just clean up my mess here. Okay, and we'll just delete this stuff and see as we've looked at it so we can keep a buffer expression on the page. Oh, I guess it was already there. So at this time, what would happen if we added in some HBr, that's hydrobromic acid. Well, the hydrobromic acid, of course, is an acid. That's one of the first things to ask yourself. What is the invading chemical? Is it an acid or a base? It's an acid. An acid will therefore react with a base, and it's the base in the buffer designed to protect the solution from a sudden dramatic change in pH. That base is, of course, the hydrogen phosphate. And so we see an acid-base reaction again. The HBr reacting with the HPO4. Proton transfer from the acid to the base. And so that base, as we see in the original buffer expression, when it picks up a proton from hydronium ions, it turns into its conjugate partner. That's exactly what it's going to do. It doesn't care who it gets the proton from. It's going to turn into its conjugate. So H2PO4. And then we've got the conjugate of the acid, that bromide ion, kicking around in solution. So we have neutralized the acid that was trying to drop pH. We have produced a small amount of the conjugate acid, and so pH still drops slightly. But instead of dropping by maybe 3 or 4 pH units, it drops by maybe 0.2 or 0.3 pH units. So it's resisting that change to pH, and there's a very modest drop in pH because of the action of the buffer. Let's look at another one. Okay, here's the next one. And if you like, pause the video for a second and try this one for yourself. New buffer system in place. Identify the conjugate pair. Identify the acid and the base of the conjugate pair. Then write an equation to explain what happens if HNO3 is added to the buffer. Okay, we'll assume that people have paused and tried this for themselves already. Let's go with orange this time. So identifying the conjugate pair, it's the non-water conjugate pair. The water is principally just the solution, the solvent, but of course it is capable of exchanging protons with the conjugate pair. As we look at that conjugate pair, it's HCO3 along with the CO3. Now to turn into its conjugate partner, the HCO3 has to give away a proton. It's the acid of the buffer. Won't always be written on the left, sometimes it will be on the right, depending how I set it up. Now conjugate partner, picking up a proton from hydronium ions, is the base of the buffer. Just as the HCO3 donates a proton to water in the forward acid-base reaction. So there's two separate reactions, two separate examples of a proton transfer. The HCO3 is the acid of the buffer, the CO3 is the base. So adding HNO3, of course that's one of our acids, our monoprotic acid. So that HNO3, that nitric acid, being an acid, can only be neutralized by a base. We have already identified the base of the buffer. So that's the one chemical that can help us out. Acids do not react with other acids. They only react with bases. And we've got the base of the buffer. And so we'll see a proton transfer from the acid to the base. So the acid, losing its proton, it turns into its own conjugate form, the nitrate ion, which we saw from chapter 4. And the carbonate, which most of the time, idling, will just pick off protons from hydronium ions to form the HCO3. Now picking off a proton from this acid, it's going to be the same result. It's going to be HCO3, the hydrogen carbonate. Doesn't care where it gets the protons from, it turns into its conjugate form all the same. So we have neutralized the acid, the nitric acid that was added, neutralized it, but still produced some of the conjugate acid of the buffer, HCO3. So pH will still drop slightly, but it has resisted that drop compared to having a solution without the buffer. That's all the buffer can do, buy us time and resist changes in pH. Okay, let me clear this up and we'll look at one classic example in the body. Okay, in your daily diet, of course, you're consuming food, and that food is combusted in the body with oxygen from the lungs to produce energy, ATP, and we get byproducts of water and carbon dioxide. Excuse me, my pen working here. And let's switch to purple. So that CO2 produced is often exhaled out of the body, but some of it does become trapped in the bloodstream, in the blood plasma, where it mixes with water to form carbonic acid. That carbonic acid, as an acid normally would do, it donates protons to other molecules of water in the blood plasma to produce hydronium ions, which could make the blood plasma acidic. So we have a conjugate pair in the blood plasma to control pH. If we're looking at this overall equation here and looking at the extremes, products divided by reactants, we could write the acid ionization constant as the hydronium ions multiplied by the hydrogen carbonate divided by the CO2. Of course, water ignored in an aqueous system. And if we want to work out what's happening to pH, we rearrange the equation to make the hydronium ions the subject. And so the acid ionization constant multiplied by the CO2 concentration divided by the hydrogen carbonate concentration gives us that hydronium ion concentration. Because we can take the negative log of that hydronium ion concentration to give us pH. As we mentioned at the top of the video, the pH of blood plasma is usually about 7.4. And that buffer is in place in the blood plasma to maintain that pH and resist changes. But sometimes too much of that carbon dioxide makes its way into the blood plasma. Of course, we can see from Le Chatelier's principle, if we look at the equation, if we increase the concentration of a chemical, equilibrium moves away from that chemical. Equilibrium would move to the right. Too much, we move away from the chemical, so we produce a greater concentration of hydronium ions, and the acidity of the solution could increase. pH could drop. So how does the body combat this? Well, this is what we call respiratory acidosis. And this is often something that happens when we have respiratory failure and we're not able to expel enough CO2 from our body. And then sometimes it's a side effect of people who have advanced lung disease. So to combat this and this respiratory acidosis, the patient would have to be connected up to an intravenous drip with some hydrogen carbonate to neutralize that excess acid. On the other hand, sometimes people can be the victims of a traumatic experience like a car crash, and that can cause people to hyperventilate. And when they're hyperventilating, they're actually exhaling too much of the CO2, and there's very little of it making its way into the blood plasma. So if we don't have enough chemical, Le Chatelier's principle tells us, if we remove a chemical, equilibrium moves towards that chemical. That movement from right to left would decrease the concentration of hydronium ions in the blood plasma. It would increase pH. And this is what we call respiratory alkalosis. And so to combat that, at the scene of the accident, we can often just give the patient a paper bag to breathe in and out of. They'll start to re-inhale that CO2 that they've been hyperventilating, exhaling. And as they reabsorb the CO2, that will increase the concentrations of CO2 in the blood plasma, and pH will start to drop again back to its normal level. Remember, it doesn't take much change to cause problems in the blood plasma. A pH rise or drop of about 0.1 of a pH is enough to start to give a patient problems. Okay, that's it for chapter 9. We'll be doing lectures all this week, of course, and we've got the final exam next week. Office hours, as normal, at 9:30 each night.